We have seen, sorry, we have seen how parallel plate waveguide can guide electromagnetic waves as transverse magnetic and transverse electric modes. And we said that in the case of parallel plate waveguide, the TE and TM waves can be represented as multiple reflected waves between the two interfaces of the parallel plate waveguide. In the case of the parallel plate waveguide, we have two conducting planes separated by a dielectric material, and this dielectric material can be air. The question now is, what will be the situation if you have one grounded plane and above this grounded plane there is a dielectric slab. The dielectric slab has a dielectric constant epsilon r greater than unity. Before going in this configuration, let me remind you by total reflection. We have studied in the book of Engineering Electromagnetics the reflection and transmission from one dielectric material to another dielectric material. And we have said that the relation between the incident angle, theta incident, and the transmitted angle, theta transmitted, is called Snell's law. And Snell's law, in the notations of the book of Engineering Electromagnetics, is N1 sine theta 1 equals N2 sine theta 2, where N is the refractive index of the material, which corresponds to square root of epsilon r. So if we are talking about medium, 1 is the incident plane, so square root epsilon r theta incident equals 1 sine theta transmitted, assuming that the wave is coming from medium of epsilon r to medium of free space of epsilon naught. And according to this relation, we can obtain cosine the angle theta 2, cosine the transmitted angle, as square root of 1 minus sine square theta 2, where theta 2 is the transmitted angle. And according to Snell's law, sine theta 2 can be represented as N1 over N2 sine theta 1, or in terms of epsilon r, square root epsilon r over 1 sine theta incident. So cosine theta transmitted equals square root 1 minus N1 over N2 squared sine squared theta 1. I want to draw what is theta 1 and theta 2. So this actually, sorry, this theta 1 and this theta 2. Okay, and this is the incident and this is the transmitted. Okay, so cosine theta 2 or cosine theta transmitted equals square root 1 minus N1 over N2 squared sine squared theta 1. In our case, N1 over N2 correspond to square root epsilon r. So N1 over N2 squared is epsilon r. and epsilon r is assumed to be greater than unity. So in this case, at specific angle, the value of sine theta 1, sine square theta 1 multiplied by epsilon r would equal 1, and in this case, cosine theta 2 would be 0, which means that theta 2 would be 90 degrees. In this case, the transmitted wave will be grazing on the interface between the lower dielectric medium and the free space. The question is, what will be the situation if theta 1 is greater than this value? If theta 1 is greater than this value, so epsilon r sine squared theta 1 would be greater than 1, and in this case, the argument of the square root would be negative. So this value, the square root of negative value, would be imaginary, and this will correspond to non-physical angle, or in other words, there will no real angle that correspond to the transmitted angle. In this case, all the wave inside the dielectric medium will be reflected back inside the dielectric medium. So the angle at which n1 over n2 square sine squared theta 1 equals 1, we are calling this angle is the critical angle. So the critical angle, sine theta critical, equals n2 over n1, such that n1 over n2 multiplied by sine theta critical would be unity. And if the incident angle is greater than theta critical, then will be total reflection inside the dielectric. So if sine theta 1 is greater than n2 over n1, the intrinsic impedance of medium 2 and theta 2 would be imaginary, and in this case the reflection coefficient would be something imaginary minus something real over something imaginary plus something real. So the magnitude of the reflection coefficient, it would be unity with a specific phase shift, and this is called total reflection. So at a single angle greater than the critical angle, electromagnetic wave can be total reflected at the interface between the dielectric and air and reflected back to the conductor, and from the conductor it would be reflected back to the interface between the air and dielectric, and then it would be reflected once again, and so on. This is actually the same behavior as in the case of the parallel plate waveguide. This is multiple reflection inside the dielectric medium, and this multiple reflection does not penetrate to the free space. So the wave is guided along the dielectric slab. And in this case, the electromagnetic waves are located at the interface or at the surface between the dielectric medium and the free space and cannot penetrate to the free space. So we are calling these waves as surface waves. And these surface waves can be transverse magnetic or transverse electric. In this video, we are going to study transverse magnetic modes in grounded dielectric slab, or transverse magnetic surface wave modes in grounded dielectric slab. And in the following video, we are going to study the transverse electric surface wave modes in grounded dielectrics. So let us start with transverse mode or transverse surface wave mode in grounded dielectrics. If I'm talking about transverse magnetic mode, this means that the longitudinal magnetic field in the direction of the propagation would be 0. However, we have longitudinal electric field component. So assuming that the direction of propagation is z direction, in this case, we have Ez, longitudinal component, as a function of x, y, and z. The function of z is the propagation function, e to the power minus j beta z. So the remaining part is the modal function, small ez, as a function of x and y. And because the geometry of the structure is independent on y, so we are expecting that the function of Ez as a function of y is constant and is only function of x. Now, by applying Helmholtz wave equation for the case of guided waves, which is nabla t squared Ez plus kc squared Ez would be 0. Nabla t squared in this case would be just the differentiation with respect to x. So it would be partial by partial x squared plus kc squared. The question now, which is kc? We know that kc squared is k squared minus beta squared. But in the present case, we have two values of k. We have k inside the dielectric medium, and we have another k in the free space. Inside the dielectric medium, k equals epsilon r k naught. And in the free space, it is k naught direct. So, in this case, the Helmholtz wave equation in the dielectric medium, it would be nabla t squared plus epsilon r k naught squared minus beta squared Ez equals 0. In the free space, it would be partial by partial x squared k naught squared minus beta squared Ez equals 0. So, this differential equation is valid for x from 0 to d, and this differential equation is valid for x from d to infinity. Effectively, this value, epsilon r k naught minus beta squared, should be positive, such that the wave would be propagating inside the dielectric slab. However, this value should be negative, such that the wave is decaying exponentially along the x direction outside the dielectric slab. So, in the case of a propagating mode inside the grounded dielectric slab, the wave is propagating in the dielectric media and evanescent decaying outside the dielectric media. This can be satisfied if the value of epsilon r k naught minus beta squared is positive and k naught squared minus beta squared is negative. Or in other words, we can say that epsilon r k naught squared is greater than or equal beta squared, and beta squared is greater than or equal k naught squared. We are going to call or to make a notation for epsilon r minus k naught epsilon r k naught squared minus beta as k cutoff squared, while the negative of this value, which is beta squared minus k naught squared, is h squared. This means that this differential equation is partial by partial x squared plus kc squared Ez equals 0 in the region of x is greater than 0 and less than d, and on the other hand, partial by partial x squared minus h squared, because h squared is beta squared minus k naught squared, so minus h squared Ez equals 0. The solution for partial by partial x squared plus kc squared Ez as a function of x it can be represented as sine kcx and cosine kcx. So if we take the second derivative of sine kxc, it would be minus kc squared sine kcx. So minus kc squared plus kc squared, it would be 0. Okay? But for the case of partial x squared minus h squared, the solution would be either e to the power hx or e to the power minus hx, such that if we have differentiate twice, it would be h squared ehx. So this would be h squared minus h squared, it would be 0. As I said, k squared minus beta squared is minus h squared. Alright? So the solution of the mode function Ez in the region x greater than d and less than infinity is e to the power hx or e to the power minus hx. Now we have four unknown coefficients a, b, c, and d. And these coefficients, in addition to them, we have the value of beta. And according to the value of beta, we can determine kc and h. So we have 5 unknowns. Okay? It is required to determine these 5 unknowns by using the boundary conditions. At the beginning, Ez is tangential to the ground plane at x equals 0. And we know that the tangential component of the electric field at the ground plane or the perfect electric conductor should be 0. So in this case, Ez at x equals 0 should be 0. At x equals 0, it is according to this equation. We are going to apply x 0. So the sine is 0 and the cosine is 1. So in this case, the value of V would be the value of the electric field should be 0 because the tangential electric field is 0. So the first boundary condition is that the tangential electric field at the plane x equals 0 is 0. Thus, the value of B should be 0. On the other hand, according to the radiation boundary condition, the radiation boundary condition states that the field at infinity should be vanishing or at least constant. It cannot be increasing. And here, when x tends to infinity, the exponential term e to the power hx would be infinity. So this term does not satisfy the radiation boundary condition. Thus this term should be 0. This means that the value of C should be 0 to satisfy the radiation boundary condition at infinity, at x equals infinity. Okay? So now by using two boundary conditions, one at x equals 0, we obtain B equals 0, and the other one, x at infinity, we obtain C equals 0. The remaining parts are A and D. Okay? That's what I have said. Ez at x equals 0 should be 0, thus B is 0, and Ez should be less than infinity as x tends to infinity, thus C equals 0. The other boundary condition is that here we have an interface between air and dielectric medium. And we know from the boundary condition of the interface between two dielectric medium is that the tangential electric field should be continuous. Thus, the tangential electric field inside the dielectric medium at x equal d should equal the tangential electric field at here at x equal d. And the tangential electric field in the present case is Ez. So in this case, Ez at x equal d from this relation should equal Ez at x equal d from this relation. And already we have proved that B and C are 0. So in this case, A multiplied by sine KCD should equal D multiplied by e to the power minus HD. A sine KCD equals D multiplied by e to the power minus HD. So we have now a relation between A and D. Another relation can be obtained by applying the boundary condition for the tangential magnetic field at x equal d. Because we don't have a surface current on the air dielectric interface in the present case, so the tangential electric field at x equal d inside the dielectric medium equals the tangential magnetic field, I have said electric field, sorry, the tangential magnetic field at x equal d inside the dielectric medium should equal the tangential magnetic field at x equal d in the air. And the tangential magnetic field in the present case is Hy. And Hy, it can be obtained from Ez by differentiating Ez with respect to x. So Hy is proportional to partial Ez by partial x. Partial Ez by partial x in the present case, in the above equation, it would be A Kc cosine Kcx. And in the second equation, partial Ez by partial x, it would be minus Hd e to the power minus Hx. Now, by equating the two derivatives at x equal d, it would be also we have the relation between Hy and Ez. Hy is proportional to epsilon r partial Ez by partial x. So we have here epsilon r A Kc, and here we have Kc squared. So Kc over Kc squared would be 1 over Kc cosine Kcd. This would equal d multiplied by minus h over h squared. So this would be d over h e to the power minus hd. So by applying the continuity of the tangential magnetic field Hy at x equal d, we can obtain this relation. Now we have two equations and two unknowns. The two unknowns AD. By dividing equation 1 over equation 2, we can obtain a relation between Kc and H. And effectively, Kc and H are already related by beta. So, in this case, before going to these relations, we here are going to represent the total or the field components of the transverse magnetic surface wave modes inside the grounded dielectric slabs. in terms of the modal function Ez inside the slab and outside the slab. Inside the slab is A sine kcx, outside the slab is d e to the power minus hx. The electric field Ez, the total electric field Ez would be the modal function multiplied by the propagating function e to the power minus j beta z, and at x greater than d it would be e to the power minus hx e to the power minus j beta z, and here we have applied the relation between A and D, which we have already obtained, that D equals A sine kcd multiplied by e to the power hd. We have removed D and applied D equals A sine kcd e to the power hd. So A sine kcd e to the power plus hd, this is D. Okay, this is Ez in the region inside the slab and outside the slab. From Ez we can obtain Ex. Ex would be the derivative or proportional to the derivative of Ez with respect to x. So it would be here proportional to cosine kcx, and here we have kc, and already we have kc squared in the denominator. So kc over kc squared would be 1 over kc. So it would be minus j beta over kc a cosine kc e to the power minus j beta z. In a similar way, here it would be minus j beta over h, and here this is the derivative with respect to x. It would be minus h, over minus h squared. So this would be 1 over h, and the remaining part is the same. For hy is minus j omega epsilon over kc squared partial Ez by partial x. So in this case it would be partial Ez by partial x would be kc a cosine kcx, and we have kc and kc squared. So it would be minus j omega epsilon naught epsilon r over kc a cosine kcx e to the power minus j beta z. In the air region would be minus j omega epsilon naught over h a sine kcd e to the power minus h x minus z e to the power minus j beta z. It can be noted here that all the field components now are in terms of the amplitude A. The question is, what is the value of beta? What is the value of the propagation constant? This is the remaining unknown. And this remaining unknown would be determined from the relation that we already obtained between A and D. And these two relations, by dividing equation 1 by equation 2, we can find out that sine kcd over cosine kcd, it would be 10 kcd, and here 1 over 1 over kc, it would be kc, and this epsilon r would be in the other side. Here d over d e to the power minus 1 h e to the power minus 1 hd will be eliminated. Here 1 over h would be h. So the relation between kc and h according to the boundary conditions is Kc tan Kcd equals epsilon RH. To make the equation slightly balanced, we are going to multiply both sides by d. So Kcd tan Kcd equals epsilon R HD. Okay, and already we have the relations between Kc and H and B and beta as Kc squared equals epsilon R K naught squared minus beta squared, and H squared is beta squared minus K naught squared. This originally from the Helmholtz wave equation at the beginning of our discussion. If we are going to add these two values, so minus beta squared would be eliminated by beta squared. This can be expressed as Kc squared plus H squared equals epsilon R minus 1, epsilon R minus 1 multiplied by K naught squared. Or in other words, we can represent it as Kcd squared plus Hd squared equals epsilon R minus 1 K naught d squared. Effectively, if I am talking about the plane consisting of x coordinate as Kcd and y coordinate as Hd, this equation would represent as a circle whose center as 0 and 0, and its radius is the square root of this value. So this circle or this equation is equation of a circle in Kcd HD plane with a radius equal square root of this value, square root epsilon R minus 1 K naught d. So now we have two relations, one coming from the boundary conditions and the other is coming from the Helmholtz wave equation. By solving these two equations, which are not linear equations, they are non-linear equations. So by solving these two equations, we can obtain what is the value of beta, which will satisfy both equations simultaneously. Or what is the values of Kc and H, which satisfy the boundary conditions and Helmholtz wave equation simultaneously. This actually can be done graphically by drawing the equation Kcd tan Kcd epsilon R equals epsilon R HD in the plane Kcd HD, and drawing the circle Kcd squared plus Hd squared equals epsilon R minus 1 K naught d squared, and the intersection of these two equations would represent the solution. This is actually what we are talking about. We have now two equations. Let us say that it is Kcd and Hd, Kc squared d, H squared d. Okay, and this is the plane Kcd HD, and this is a circle whose radius is square root epsilon R minus 1 K naught d, and the relation Kcd tan Kcd equals epsilon R HD. We have here the value of Kcd. So I'm saying y equals x tan x. Okay, I'm at a certain value of x, which is Kcd. From this value of x, I obtain the value of tan x and multiply it by x to determine the value of y, which is Hd. By doing this, we are going to draw the function HD or HD equals 1 over epsilon r KCD tan KCD. The value of tan equals infinity when the argument is at pi over 2, and the value of tan is positive for x is positive and is negative for x is negative. So at negative x, here negative multiplied by negative, it would be positive. So the function KCD tan KCD is even function. Even function means that f of x equals f of minus x. So it is even function, and it is positive in the range from 0 to pi over 2. As the value of pi over 2 reaches to infinity, greater than pi over 2, greater than pi over 2, the value of tan it would be negative, and the value of KCD is positive. So negative multiplied by positive would be negative value until it reaches pi. On the other hand, if I'm talking KC negative, so tan negative KCD and KCD is greater than or less than minus pi over 2, so it would be positive, but multiplied by negative value it would be negative. And as I said, in general, the function KCD tan KCD is even function. So any point in positive value has the same point in negative value. Okay, so this is the representation or the drawing of the function HD equals 1 over epsilon r KCD tan KCD. Now, to satisfy two equations, this should be the intersection between the two equations, the equation of the circle and the equation of x tan x. So these 2 points represent the solution of these two equations. And from this solution, we can determine the value of KCD and the value of HD. And from the value of KCD and the value of HD, we can determine the value of beta, because if I have known the value of KC, I can determine beta, or I have the value of H, I have determined beta. So from this intersection, we can obtain Kc, which is the cutoff wave number inside the dielectric medium, and Hd, which is the evanescent propagating or the evanescent wave function in the air region. We can determine the value of H and Kc, and from H and Kc we can determine the value of the propagation constant beta inside the grounded dielectric slab. And by solving Kc and H to obtain the value of beta, now we obtain all the unknown functions of the solution of the two Helmholtz wave equation inside the dielectric medium and outside the dielectric medium. Okay. All right. We should look at this circle. Effectively, this circle in the KCD plane and H plane, its radius is square root epsilon r minus 1 k naught d. And effectively, k naught is omega over c. So it is 2 by f multiplied by square root mu naught epsilon naught. It can be noted here that At any value of K naught D, we have intersection point. At any value of K naught D, we have an intersection point. This means that at any frequency, because this radius is proportional to the frequency, D is constant, epsilon r is constant. What is variable here is the frequency. So at any frequency, we already have solution for the value of HD and KC. This means that the transverse magnetic mode can propagate starting from the DC. Or in other words, at any frequency, the grounded dielectric slab support the dominant mode or the lowest cutoff mode of the surface wave mode inside the ground dielectric slab. Okay? So the cutoff frequency of TM0 mode is 0. This means that we always have transverse magnetic mode or transverse magnetic surface wave mode in grounded dielectric slab. The question is, what will be the situation if the frequency increases? If the frequency increases, the radius of this circle will be increased. We still have intersection here. But after a while, we will have intersection also here. Okay? What is the difference between the intersection point here and the intersection point here? Assuming that we have a circle like this. What is the difference between this point, for example, which is a solution, and this point? At this point, we have H is positive. And already we have proved that, or we have assumed that the field is at x greater than d is proportional to e to the power minus hx. So in this case, the value of h is positive corresponds to decaying wave. But here the value of h is negative, in the negative side. If the value of h is negative, this means that e to the power minus negative something multiplied by x is negative, it would be positive. So it is e to the power positive value of x. So if x is increasing to infinity, the field would be increasing to infinity. So mathematically, these 2 points correspond to a solution for this equation, for these 2 equations. But physically, these 2 points correspond to growing wave. And effectively, growing wave does not satisfy the radiation boundary condition. So physically, these 2 solutions are not accepted. So we only accept the solution for the positive H. So as the frequency increases, we have improper pools or improper solutions. Improper are not suitable. But after a while, there will be, for example, let me draw it. If I have a greater circle, sorry, what happens? If I have a greater circle, then I have 2 positive poles. This one pole and this another pole. This one pole and this another pole. This pole corresponds to the transverse magnetic 0 mode, and this pole will correspond to the transverse magnetic 1 mode, TM0, TM1. This means that by increasing the frequency, we will have more than one propagating transverse magnetic modes. And for all the propagating transverse magnetic modes, the value of H must be positive. If H is negative, this is not proper or improper mode, which is not suitable because it does not satisfy the radiation boundary conditions. Is that what I'm saying here? For any non-zero thickness sheet with a relative permittivity greater than unity, there is at least one propagating transverse magnetic mode, which we are going to call it transverse magnetic zero mode. This is the dominant mode of the dielectric slab waveguide, and it has zero cutoff frequency. It can be seen that the next transverse magnetic mode, TM1 mode, will not be to propagate until the radius of the circle become greater than pi. If the circle here if the circle is greater than pi, we have another pole. If the radius of the circle is greater than pi, we have another pole. This means that the first pole is 0, the second pole when square root epsilon r minus 1 k naught d is greater than or equal pi. If I'm talking in terms of frequencies, is 2 pi f over c. So the cutoff frequency of the first mode is 0, n equals 0. The cutoff frequency of the first mode, 1, it would be c over 2d square root epsilon r. How comes? Here 2 pi fc, 2 pi f over cd square root epsilon r equals pi. So the pi will be eliminated with the pi, and we have c d 2d square root epsilon r. In general, the cutoff frequency of the nth mode, it would be n c over 2d square root epsilon r minus 1. Usually, we are not interested in surface wave modes, but because the transverse magnetic zero mode, surface wave mode, has zero cutoff frequency, in any structure consisting of grounded dielectric slab, we already have this surface wave mode. Even so, we don't need it, or we are not interested in it. But because we are not interested in this surface wave mode, we are not interested in the higher modes. So in designing a grounded dielectric slab, we are interested not to introduce the higher order modes, or not to excite the higher order modes. This means that we are going to make the value of d is much smaller than the highest frequency, or the usable highest frequency. So as an example, if I'm interested in using a ground dielectric slab of epsilon r, for example 4, and we are talking about frequency 10 gigahertz, I should use the value of d less than 1 multiplied by c over 2 multiplied by the frequency square root epsilon r minus 1, such that I don't excite the higher order transverse magnetic surface wave modes. Okay, all right.